All right, here we go. Section 4.7. We're going to talk about our inverse trig functions and the integration of those trig functions. So we have three that we normally talk about. If we have the integration of 1 over the square root of a constant squared minus a variable squared du, that's going to integrate into the arcsine of u over a. So that variable, whatever this here is, divided by the constant plus c. If we have 1 over a squared plus u squared, the integration of that, then we have 1 over a arctangents of u over a plus c. Integration of 1 over u, square roots of u squared minus a squared. Again, u is our variable there. A is going to be our constant. Then we have 1 over that constant arcsecant of the absolute value of u over a plus our c. So when we look at these, you can probably expect to have one of them on your AP exam. If I'm going to guess, and there's one that I want you to focus in primarily on, that would be that 1 over a squared plus u squared. It seems like they like that one more than the other two. However, any of those are going to be game as we go forward on quizzes and tests. So the first thing you got to make sure that you do is figure out what that a and that u are. Remember, we want a number squared minus a variable squared. If we don't have just a variable squared, we have to make it into a variable squared in order to be able to get into our inverse trig functions. So we'll start out with a somewhat easy one here. We have 8 over the square root of 16 minus x squared. Remembering 16, that's a perfect square, so that gives us 4 squared. And then if you want, you can do this x squared as well. So here we have an a value as being 4 and a u value as being x. Again, not miserably important that we see that or remember that. However, we know this is going to go into then an arcsine because I have a number minus my variable. Remember the other ones, we have a plus here, and the other one, the arcsecant, gives us a variable minus the constant. So I have arcsine of what? I have the arcsine of my u, which is x, divided by 4 plus c. And that's, by definition, going to be our answer. Oh, wait a minute, I forgot my 8, didn't I? Yeah, I forgot my 8. Whew. We also can bring that 8 out there as well, can't we? So we can write this as 8 integrations of 1 over the square root of 16 minus x squared dx. So I do have that 8 out there. Sorry, didn't make that mistake on that one. All right, just a couple more examples, several examples actually, and we'll see some different things that possibly could happen with us. So here we have 8 over 16 plus x squared. So we do have the addition. That 8, I'm not going to forget that this time. So we're going to write this as 8 times the integration of 1 over 16 plus x squared dx. 16, that's going to be 4 squared, and then plus our x squared. So I see this as an arctangent because I have a number squared plus my variable squared. So that's going to be 8 times 1 over my a value. In this case, my a value is 4. So I have 8 divided by 4 times the arctangent of my u, which is x, over my constant square root there, which is x over 4 plus c. We can reduce that 8 over 4 as being 2 arctangents of x over 4 plus c. Now we come into some problems that maybe aren't as nice and clean and easy as we would like them. So here we have x squared plus 9. When I see x squared plus 9, I see that as a variable squared plus a constant squared, which I could rewrite this as 9 plus x squared. That in my mind throws in arctangent. However, up here, I have x plus 2. That doesn't work for me, does it? So we got to think about what we can do with this to make it something that we can work with. Well, if I do a u substitution, it doesn't have to necessarily be an arctangent problem. So maybe I do a u and I try this and I see what happens. I get 2u equals 2x dx. Well, that's sorry, not a 2u. I get du, equals 2x dx. So if I look at this x plus 2 dx, I don't have that plus 2 over here to work with. So this is my first inclination that, hey, this isn't just a u substitution problem. So I need to come back here and think about, well, what can I do with this? Well, one thing, I see this addition up here, this x plus 2. So that tells me that I can go ahead and break this up into two different integrations. And the reason I'm going to do that is because, remember up here, I let my u equal x squared plus 9, so my du is 2x dx. I can use that x dx, can't I? I see that right here. So I'm going to go ahead and bring this u back in. This u equals x squared plus 9, du equals 2x dx. Because I can divide this 2 over, so I get 1/2 du equals x dx. So this integration here becomes 1/2 the integration of my du, or 1 over u, du. This 2 over x squared plus 9, that now I have an arctangent, don't I? Because I know this 2 can come out to the front, so plus 2 the integrations of 1 over x squared plus 9 dx, where my a is 3 and u is my x. So I'm going to go ahead and rewrite that down here as 2 integrations of 1 over x squared plus 9 dx. That way I've got all my integrations in a line. I can go ahead and now integrate. So I know the integration of 1 over u. Integration of 1 over u is the natural log of the absolute value of u, which is x squared plus 9, plus my c. Remember that c is fluid, and I'm going to have another c over here, so I'm just going to put a plus c at the end to clean it up. Alright, so now I can go ahead, think of my a as my 3, so I've got 2 over 3, so 2 times 1 over 3, which will be 2/3. Then the arctangent of my u, which is x over that a value of 3. Again, we can put that in parentheses if you want. This natural log of the absolute value, we'll talk about that for just a second here. Since x squared is going to be always a positive, plus 9 will always be positive, this entire thing would be positive, so we don't necessarily have to have these absolute values. Not incorrect if you put them, but on a multiple choice test or quiz, you will not see those as being there. You'll see them as in parentheses. Alright, so here's a little more complicated problem, I guess, if we think about what we want to look at here. So with the first one here, at the top of the paper here, notice we have the 9x squared minus 16. So that's going to give me an inclination again that it's going to be an arcsecant. So we have no variables on the top, which is good. They're gone. So if I think about 9x squared, I think in terms of squareds, that's 3x squared, isn't it? Yes, and I have that 3x there as well, don't I? And then minus my 16, which is my 4 squared. But remember, this has to be a single variable, and this has to be a single variable out here. So we're not quite there yet. So what I'm going to do is I'm going to bring a u in as being 3x. And then my du is going to be 3 dx. So I have a 1/3 du equals dx. Now I can go and do my substitution. So I can bring my 1/3 in. I have this 2 that I can bring out. So I have 2/3 the integration of 1 over u square roots of u squared minus 4 squared du. Make sure that makes sense to you there for a second. So we replace that 3x with our u. This 3x, again, is our u. So it becomes our squared minus our 4 squared. So we then can go ahead and write this now using our secants, our arcsecants. So what is that? That's going to be our 2/3 of, or 2/3 times, our 1 over our a value, which is 4, times the arcsecant of the absolute value of u, which I know u is going to be 3x, divided by my a value, which is 4, plus c. Now we can go ahead and clean this up. 2/3 times 1/4, that's going to give us 2/12 or 1/6, the arcsecant of the absolute value of 3x divided by 4 plus c. And there's our final answer. Yay! All right, on our next problem then, we have 2 divided by the square root of e to the 4x minus 16. Again, to me, this is going to be an arcsecant. Why do I see that? Well, I see that this is going to be e to the 2x squared minus 4 squared. So it's going to work very similar to what we just had up here. So we're going to let our u equal e to the 2x. So du is going to equal 2e to 2x dx. Remember to take the derivative of an e to an exponent. We're going to bring the derivative of the exponent e to that same exponent dx. I have a 2 dx in my original problem. So we're going to leave that 2 there, but I need to get rid of this e to the 2x. So I'm going to take this e to the 2x du equals 2 dx. We haven't seen this very often, but we do every once in a while. At this level, we can bring x's in with our du. And it might look a little ugly to us at the beginnings here, but it's okay. We're going to see something happen. So we have 1 over e to the 2x square roots. E to the 2x, that's our u. So we have our u squared minus 4 squared du. What do we know about that? What do we know about this e to the 2x though? E to the 2x is our u. So we have 1 over u square roots of u squared minus 4 squared du. This is now, yep, you're right, an arcsecant, isn't it? So we have what? We have 1 over our a value, which is 4, and then the arcsecant of the absolute value of what? Well, but our u is e to the 2x. So we have the arcsecant of the absolute value of e to the 2x divided by that a value of 4 plus c. Now, I know we've done several problems as I think about it now, with all of them as our a value as being 4. Not always going to be the case. So this could be a 9, it could be 25, it could be anything. Just be careful, it's not always 4 as I look at my problems now. Excuse me. All right, our last problem here, I'm going to go ahead and do a trig function, or a trig integration. So what do we notice here? We have 1 plus sine squared. If we have 1 plus sine squared, then that's going to give me, I'm going to write this as sine of x squared, isn't it? So again, we need to get this into a single variable. So I'm going to let my u equal the sine of x. And my du then, derivative of sine, is cosine of x, isn't it? Dx. Which I have an x dx up here. Remember also, these are in terms of x, aren't they? So we've got to be very careful, because if we change these into terms of u, we ought to go ahead and change these endpoints or boundaries into u's as well. So if we're looking at the pi over 2 as being our x value, then u is going to be equal to the sine of pi over 2. Sine of pi over 2 is 1. So we're going to go from 1 there, and we're also looking at the sine of 0. And the sine of 0, yes, that is 0, isn't it? So in this now, we've changed these into u values, so we're going from 0 to 1. Of what? Of 1 over 1 plus u squared du. I have an arctangent, don't I? So our arctangent is going to go to 1 over 1, since our a value is 1 squared there, times the arctangent of, excuse me, our variable, which is u, divided by 1, which I guess we don't need to put that over 1, do we? And then we're going from 0 to 1. All right. So now we can go ahead and plug in the 1 and plug in the 0 and subtract the two values and get our answer. So we have an arctangent of 1 minus the arctangent of 0. So what do we know about the arctangent of 1? Where does tangent equal 1? Tangent equals 1 at pi over 4. Minus, where does arctangent equal 0? Arctangent is 0. Tangent is 0 at 0. So we have pi over 4 minus 0, which is pi over 4. So our value is going to be pi over 4. And that's going to give us our final answer. So that gives you an idea of things to be looking for. I'll pull forward this here paper one last time. Again, things that you're going to be looking for is that we have variables and a constant that are going to be that are perfect squares. We also want them to be single variables as we're finding that integration. So if you have questions, let me know. Good luck, enjoy, and happy integrating.